I'd like to thank you all for coming. This is a follow-on from a press briefing we gave 14 months ago, where we were very cautious about the announcements we were making because they were a scientific announcement about the discovery of some superdielectric materials which can store remarkable amounts of electricity, far beyond anything that we've seen before. And for the last 14 months, we've been working to verify whether the materials actually work in the real world. And today we're going to give you an update as to the progress we've made in verification of that science. There are a lot of people here from different backgrounds, and this is a University of Surrey and a University of Bristol press briefing. So there's going to be a variety of people with different backgrounds in scientific knowledge. So for the scientists, I apologize if we're a bit light in the science, and for the non-scientists, I apologize if there's too much science. We're never going to keep everyone happy. So there are some great brains in this room right now, and they're fantastic scientists. And we've tried to prepare to answer every question possible that you might ask. But my daughter, who's in her final year of electronics engineering at York, asked me the most contentious question at every board meeting we've had since we formed the company. And she said, "What kind of biscuits are we going to get?" So 14 months ago, Augmented Optics and Bristol and Surrey made their first release, and some of you were present there. Because of the performance of the materials, we've changed the name of the company from Augmented Optics to Superdielectrics. And what you're going to hear today is embargoed until midday today. So I'd just like to introduce the founders and management of the company. I've worked with Dr. Highgate for nearly 20 years, mainly in energy storage technology. And Dr. Highgate developed the materials that were in soft contact lenses. And also, he was the inventor of the materials at a company called ITM Power, which in my opinion is probably the world leader in hydrogen technology. Nigel Spence is our finance director. He studied chemistry with me at school and was in charge of developing the best explosives that the school could make. So, I don't know if I can get this thing to work. So very quickly, some of you will know that we formed the company. We actually started thinking about the company about 7 years ago, and we started to go through different ideas on how we could develop some new polymers, and we didn't know what the outcome of the research work was going to be. And in fact, we had some test data a long time ago, but it was so far outside credible data, we ignored it, thinking that we had made a mistake. And we formed the company in 2014, and we've been working with Bristol and Surrey, who've been subcontracted doing the research. And we recently changed the name, as I said, to Superdielectrics, and we've discovered materials that have important implications for energy storage and supercapacitors. And I'd like to now pass it over to Dr. Highgate to take over from me, if that's okay.
Thank you, Jim. Good morning, ladies and gentlemen. My function here today is essentially to set the scene and to give some indication of the background science that has now materialised and has been mechanised in this second stage report. Basically, since I first worked with Jim 20-odd years ago, I had golden locks in those days, I remember, and much less worried. Our interest has been in energy supply and the stabilisation of energy supply, particularly sustainable energy. From a physical standpoint, there are only two basic energy systems in the universe: gravitation and nuclear in their various forms. All else is derivative, and all the renewable energies that we talk about, wind, wave, solar, are derivative of those two. They are all time varying. Gravity drives the tides via the moon, and that is at least predictable. But solar and wind are both time varying and unpredictable. And storage is therefore absolutely critical if you are to make very much use of renewable, sustainable energy resources, as indeed we can and should do. But storage is often forgotten. Our technology is based upon a platform technology which consists of hydrophilic materials. Hydrophilic materials, cross-linked hydrophilic materials, cross-linked hydrocarbon-based hydrophilic materials. My interest in these started many years ago when I and others developed simple materials which take in water in controllable amounts and they swell, as shown there in the slide. And this is the dry structure. The material consists of a matrix which is typically methyl methacrylate or acrylonitrile. That provides the long-range strength for the material, and into that and onto that you graft or impose hydrophilic sites, frequently but not universally produced from vinyl pyrrolidone. When that material is put in water, it swells. The first water goes in, ionically attaches to the hydrophilic sites, the system swells, and into the interstices between the molecules go additional free water molecules. That system, there's some examples there on the side, did make a very excellent hydrophilic contact lens. Using those materials, I and others developed a company which made the blanks, which were then turned into bespoke contact lenses. This in the period 79-80, and during that time we took a very large part of the UK soft contact lens business, at which point we were bought out, primarily I think to buy back their customers. We then went on, these materials absorb water into the structure, not onto the surface, as normal desiccants do. And as such, it made an excellent long-term wound care dressing. Examples of that. We did this for the Glaxo Group. Between them, those two businesses tot up to $3 or $4 billion a year. So they're quite significant businesses. The next question, very interested in high value added things. The next question is, can we make these things ionically conducting so that they can form the basis, for example, of fuel cells or electrolyzers? Well, the answer at the back of the book is yes, you can. You add additional moieties to this basic platform structure, and if they're sulfonic acid, when it hydrates, they will transmit hydronium ions as required in an electrolyzer. That material was patented in the early 2000s, and it has become the basis of the technology used by ITM Power plc. Jim and I, between us, and primarily Jim, took this public in, I think, 2004. Perhaps worth saying we have now no contact with that company. Next question, you've probably guessed that. Can we make it electronically conductive? Because if we can, we've covered all the bases to electronic devices. So we take the basic structure again, and in this case, we have added to it a material which I'll short form to PE dot. It's the polystyrene sulfonate version, PSS version. It exists, you can go out and buy it. It lives on the backside of the touch screen in your mobile phone, but it's very fragile chemically, doesn't like water, and you couldn't make a block of it, so it meets none of our objectives. However, it is available, and if it is integrated into our material, cross-linked and hydrophilic sites added, then when you hydrate it, it becomes electronically conductive, or at the very least electronically interesting. If you can further modify it by adding a range of commercially available imidazoles, and between these produce at least two classes of material which are called industrial grade materials. Our original objective, as you remember, was to make something that was bioacceptable or biocompatible, and somewhat to our general surprise, if you add amino acids or EDTA to that basic structure, you do get a transparent, electrically active material, which, although it has not been proven to be biocompatible, almost certainly should be. There's nothing in there that doesn't already exist in the body. So that, ladies and gentlemen, is the background to our technology. It underpins it. It's been with us some many years. We know a lot about it. And along with our friends at Surrey and Bristol, we have taken it a great deal further, at which point I would like to hand over to them to tell you how much further. Thank you.
This is some of our reports that we've just done for the company. So, progress, development and demonstration. Stage 1, January 2017, we first announced our scientific breakthrough, the development of a suite of novel superdielectric hydrophilic polymers that had exceptional electrochemical properties, had immediate application to high-capacity supercapacitors, and these quotes were made by Prof. Furman, University of Bristol, who we asked to evaluate our initial results. So that was in report 1. Stage 2, right. Stage 2, January 2018. We're now reporting the second stage of the programme. So it was essential to carry out the scientific work forward into engineering scale systems using low-cost electrode materials. Because when we did this presentation 14 months ago, the people said, that's very good, can you make devices that work? And that's the point of this presentation today. So we've confirmed that the exceptional dielectric results translate to real-world scales, and we're developing methods for the large-scale production of the membrane materials. And the point of the work is to demonstrate exceptional capacitance values using simple, low-cost, smooth surface electrodes with immediate application to our energy storage systems, because conventional supercapacitors basically are flooded with a liquid electrolyte. And in our case, the electrolyte is a solid, or like these materials here, yeah? So you need a smooth surface because you're going to press electrode against it and it won't interpenetrate. So we're not using any of the extended surface area that people have been using in other supercapacitors. That's quite an important point. If I can learn how to use this. Okay, size matters. To establish that the unique dielectric properties measured in the first stage could be validated on a larger macroscopic scale. And this is how we did it before. Prof. Furman in Bristol, we had a basically 3mm length sample of our material between two glassy carbon electrodes, and Professor Furman tested those with silver as reference electrodes and measured the capacitance. Now we've moved up to a different scale, so this Heath Robinson type thing here is one of the materials clamped to a bench, yeah? So there are two forward electrodes on the other side of it, and the black thing, square, is the material. And Swishman's got a sample of these you're going to hand round to you in a minute. I should warn you, it's got sulfuric acid in it, yeah? So don't take it out of the bag, yeah? If you want to protect your hands, it's not dangerous, but that's just a health and safety warning. And then we moved up from there to produce a pressure control device for demonstration. So that little black square there is underneath this plastic part here, yeah? And we could then connect to materials and drive them. So that's the prototype device. Energy storage in capacitor depends on two things. It depends on the capacitance, which is measured in farads per unit area of the electrode, and the dielectric properties of the electrode. And this equation is the only one equation you need to know. This university say this is all you need to remember. V is a half CV squared, yeah? So if the capacitance goes up, the energy goes up, that should be E is half CV squared, yeah? If the capacitance goes up, the energy goes up, the voltage goes up, the energy goes up too, yeah? So there's two ways to maintain the system. And capacitance for smooth surface electrode is an excellent indicator of the effectiveness of the electrolyte, free from the complexity and uncertainties of the extended monotextured surfaces used in supercapacitors. So this is how the work has gone previously. They've grown these elaborate electrodes with these fingers on them to increase the surface area and make the capacitance go up. We're not using those, we're using smooth electrodes. So the scientific test that we did in the last report, carried out by Patrick Walinski and David Furman at the University of Bristol, used very small samples and specialist electrode materials in very carefully controlled configurations. So real-world devices are engineered using lower-cost electrodes and simple geometries, i.e. ideally carbon or steel, and flat or simply textured plain electrodes. And that's what we've done, and we'll be showing you in a minute. So in stage 2, extensive testing made to establish how stable the polymer is. Can we reproduce the polymer in the membrane with a good degree of accuracy? We can, yeah. So to establish the robustness of the formulation and abduction processes of both the membranes. And we looked at different hydration solutions on the membranes. That's why that one's got sulfuric acid in it, but we've used brine and we've used NaOH and things like that as well, yeah. So we've tried the whole area about solutions. And a lot of supergrafts have to put under pressure to make the contact work well. So we've studied the effect of contact pressure on the reproducibility of the data and the value obtained, yeah. So that's the importance of guided packing systems that be used in the subsequent devices. And our next generation device has a pressure control lever on it that holds the thing down, yeah. So we haven't shown you a picture of that. It looks even more Heath Robertson than that one, yeah. In all these trials, the capacitance of the polymer was measured against smooth metal or carbon electrodes. Again, because it cannot interpenetrate the surface. And here's some of the results. So with 301 stainless steel, we can get a capacitance of 4 farads per centimetre squared. With 904 stainless steel mesh, we can get about 1 farad per centimetre. The carbon block's about 0.02 of a farad. So the best results of 301 stainless steel are generally above 1.5 farad per centimetre, and those of 904L stainless steel maybe over 0.2 using flat, non-extended surface electrodes. You need to compare these with the air capacitance of commercial supercapacitors, which is 0.3 farad per centimetre. So our worst one is as good as, not better than the commercial ones. And they're using extended surface electrodes that we're not. So that's quite an important thing. Well, we can get it bigger. We can get capacitance of 4.82 farads, then using asymmetric stainless steel electrodes with a manganese dioxide treated surface, we can get 15.76 farads, which is outstanding. So it's been found possible to substantially increase the capacitance values of these systems using electrodes treated with manganese dioxide. Manganese dioxide is known to be supercapacitive, so it helps. So using the same membrane at 2 volts, capacitance can increase from a maximum of 4 farads to 11 to 20 farads per centimetre. Good. So the conclusions from the Surrey report. The results obtained here show that at macroscopic by real-world scales, over the sizes of actual prototype capacitive devices, SP's novel polymer electrolytes perform broadly in accordance with predictions of the scientific studies reported earlier in Report 1 by Prof. Firmin and the University of Surrey in Bristol in 2017. Actual results up to 4 farads per centimetre have been repeatedly achieved against solid stainless steel foil and 0.9 farads per centimetre squared against steel mesh. Equivalent to 1.8 farads per centimetre squared. And analysis is made for the reduced area of contact of the mesh. So obviously if you've got holes in the system, you're not making as much contact naturally. Yeah. The data taken with advanced coating systems, details withheld prior to filing, based on manganese dioxide, suggest that significant further improvements can be achieved. Assuming the use of stainless steel foil electrodes, with thickness 0.05mm, and density 7.5 grams per centimetre cubed, these results, using smooth surface electrodes, indicate energy densities of 26 watt-hours per kilogram. That has potential to be significantly increased when we can actually use suitable extended surface electrodes with our material, which can be either made or procured, but they're compatible with special properties of our novel polymer electrolytes. So we've got to make it interpenetrate, basically, which we can do. Just a few more conclusions. The novel electrolytes developed by SD Limited clearly have potential to provide low-cost supercapacitors using smooth surface electrodes that significantly exceed the best performance of the best existing supercapacitors. And with the addition of extended surface area electrodes, provides significant energy densities competitive with existing battery technology. Because as you know, batteries charge slowly, discharge slowly, supercapacitors charge quickly, discharge quickly. So theoretically they're better than batteries, but at the moment they don't store enough energy. They can now. So we can provide alternatives to battery technology in a wide range of immediately important commercial applications, including but not limited to stationary grid balancing applications. And we've talked to Professor at the University of Surrey about a renewable grid, the supercapacitors we use to balance up load. Buffer stores to facilitate rapid charging of electric vehicles, because if everybody comes back and plugs in their electric car, all the lights go out, which is kind of not what you want, yeah? So, otherwise, exceptionally high drain on local electricity grids. In addition to the direct use in transport applications, rapid recharging vehicles, critical points, and finally, by no means least, in consumer electronics. Okay, so I'll pass over now to Dr. Ian Hamerton, who'll tell you about the University of Bristol stuff.
Okay, thank you. As I say, my name is Ian Hamerton. I was formerly at the University of Surrey. I'm now at Bristol. At this stage, the important sort of step for us was to look at the data that were being presented by Brendan and the team to examine how those data stood up in sort of semi-independent scrutiny. So we can confirm that the results that we saw, that we examined, basically are highly competitive when you start comparing these materials alongside current commercial supercapacitors. As we said, Brendan's already mentioned the figure of 0.3 farads per square centimetre for commercial porous surface electrodes. The point that's worth making again is that these are not on porous structures. These are on smooth electrode surfaces where you're not getting the benefits, the additional benefits of those highly structured surfaces. So if we're getting these sorts of strong properties on these flat surfaces, smooth surfaces, then there's a lot more potential, no pun intended, in the tank when we start to sort of move from these more crude systems into more sophisticated. So once you start moving towards a commercial off-the-shelf porous carbon surface, it's comparatively easy then to move, certainly to get a 100-fold increase. That's a comparatively easy demand, just simply on the basis of extended surface areas. When you start to couple that with something like a material with a pseudo-capacitive element, we've already talked about manganese dioxide, or oxides of manganese, that's when you're starting to get towards the figures where you can begin to go from 100-fold up towards 1,000-fold. When you're in that sort of area, and again, we're talking about conventional off-the-shelf technologies, off-the-shelf materials to achieve that, then you're getting towards a potential which brings you up to 22 farads per square centimetre. Once you're in those sorts of, that sort of ballpark, then on the basis of the areas that we've been talking about, then you get an energy density of up to 180 watt-hours per kilogram. And that means that when you couple the comparatively, as Brendan said, Heath Robinson and lab scale developments and productions into a more commercial environment, when you're talking about larger structures, when you're routinely producing larger membranes, then you're beginning to get towards something which has got some sort of real commercial appeal. So, we had a look at the electrical data presented, 2 batches of commercial mono. The important thing, of course, is that if we are talking about a material that's going to be useful and usable, then we need to be able to guarantee a level of purity and that the materials don't fluctuate in terms of their quality and that they're fairly forgiving of changes in batch to batch quality. And indeed, materials were examined that were fresh out of the jar, materials that had been in the laboratory and been used to produce earlier materials. There wasn't a significant difference in the magnitude of the results, even after a period of storage of some 10 months. So that's important if you're talking about supply, having stacked a material and then formally altering it. So we're talking about materials, as we said. We're going to pass the material around in a short while. As you'll see, this material contains trace of 5 molar sulfuric acid. As Don's already mentioned, the material has been examined in a variety of different fluids. But over that sort of period of time, up to 7 days in contact with 5 molar sulfuric, not insubstantial quantity of acid, the materials are safe, stable, reproducible results. So in terms of the next stage, and the next stage is to start talking about taking this laboratory material into something which is going to bridge the gap between a usable technology, then we have to think in terms of how might one configure that. So the 3 types of cell groupings that we might examine in order to make that a reality. The first is a single cell, which has a fixed voltage and therefore a fixed energy storage capacity. So a 1.5 to 2 volt PDF would give you something which is essentially going to be dependent on the size of the membrane. It's proportional to the area involved. If you start to move that into a series stack, a series of cells stacked together, then you have the potential to control the voltage and thus the energy storage. So you might see, again, 1.5 to 2 times the number of cells proportional to the total area involved in the configuration. Finally, that combination, when you start to put together a combination of series and parallel cell stacks, that gives you the opportunity to not only control a controllable voltage, but thus a controllable energy storage, realistically dependent on the number of parallel cell stacks put together in the device. So this combination, a series of parallel cell group, expanded suitably with appropriate manufacturing techniques, gives you the ability to meet any voltage or storage capacity required by a specific application. And that's crucial because you can begin to see that we get towards a situation where a single cell, in this case, a membrane coated on both sides using carbon powder, so adding a surface area by means of active carbon, pressed between 904L stainless steel mesh. The choice of 904L means that it has additional stability in the sulfuric acid without corroding. Now, having charged the system for 5 minutes at 1.5 volts, that runs the fan for over 3 minutes. I should point out, if you cast your eye to the top of that system, you'll find that there's in the middle of the clamp there's a small blue square. That blue square is the actual active material. Everything else you see around you is just simply to enable that material to deliver its performance. So that's the only active component in there. You can see that physically moving. And as I say, that charge gives you a 3-minute video. I'm quite happy. I'll cut it short there so you can see it later if you wish. But moving on to greater complexity. Once you get into the stack arrangement, and this is a 3-series stack, you can see them open as a series of leaves there, each of those an individual stack. Again, membrane, carbon to increase the surface area, pressed between 904L stainless steel mesh, charged for 2 minutes at 5 volts, and that runs the LED for over 2 minutes. No voltage stabilization or ballast resistor used. And again, as Brendan's made the point, this is very much, it's a bit Heath Robinson, but what you can see there, the material clamped, very standard engineering clamp, keeping the pressure on that material, and then essentially held between acrylic just to insulate the material, that stack powering that, that glowing bulb. And I'll close it there, hand over to Jim.
So what we've done basically is we've taken it from a scientific theory to working devices, which is a big, big step forward. We didn't know if we were going to be able to do that, and the indications from Surrey Bristol reports indicate that we might be able to achieve better energy densities than existing battery technology. Now, my slides are incredibly simple, but I actually have to take notes to make sure I don't forget any important points. So, what you see, if you look at that, is a safe and low-cost supercapacitor. But the really important point to focus on is the top point, rapid recharging and discharging. This is really important. For cars, everyone's worried about electric vehicles taking a long time to charge, and if you go to refuel, you get stuck in a queue for a couple of days waiting till the next car's finished. So we do, with supercapacitors, have the potential to fill as fast as existing petrol technology. The second thing is that I use a rule called Jim's rule of electrochemistry. So this is one that Ian and Brendan aren't familiar with. Electrochemical batteries do not like to be charged by rapidly changing intermittent energy. It damages the cell structure. So, supercapacitors are compatible with rapidly changing intermittent energy, which is renewable energy. That means that supercapacitors could be the key link between renewable energy and their storage. And the final point I'd make about that, as has already been alluded to, I think, by Brendan, is that if you could take electricity and store it as a buffer, say, imagine a supercapacitor the size of a container, and you go to the petrol station. The grid can't take the high current densities going down the wires, so there will be a buffer, and it'll have to be a very big buffer, but it's got to be low cost, so that you can directly fill your car quickly from a large supercapacitor and put it into a small supercapacitor in your car. So this buffering is very important for renewable energy and refueling cars. It is a very important thing, and I think most people, again, underestimate that, because I personally think it'll probably be the biggest part of the business, not the batteries in the cars, but the buffering. And so it doubles the size of the supercapacitor market relative to an electrochemical battery. So this is the nightmare slide for me, because this is the Achilles heel. This is the Achilles heel of supercapacitors. Supercapacitors don't store much energy per kilo, about 1/20th of a lithium-ion battery. Our work from Professor Furman's report indicates that our materials can increase the capacitance by 3 or 4 orders of magnitude, which means 1,000 to 10,000 times. Last time I did this presentation, I was reluctant to put numbers on it, but it means that we could potentially get to between 4,000 and 40,000 watt-hours per kilogram theoretically. So that's roughly 50 to 500 times the energy density of a lithium-ion battery, theoretically. So we have only just scratched the surface. The second point I'd like to make is that, well, this is where my brain is going too fast for me, I'm afraid. The second point I'd like to make is that petrol stores energy for a long period of time, months, batteries for weeks, because they self-discharge slowly, and supercapacitors for days, because they discharge more quickly. So we think that for the clean future, it's going to be a combination of hybrid systems using capacitors, supercapacitors, and batteries. In the perfect world, to replace petrol, we should think of another chemical storage, and that's hydrogen. For batteries, they stay the same, and for supercapacitors, we go to a high energy density supercapacitor, and that combination of the three will get us to a CO2-free, sustainable energy future. So the two key weaknesses of supercapacitors are energy density and it's self-discharging, so it only holds energy for a few days. In fact, Nigel Spence, who's at the back, our finance director, we were describing the buses, the Chinese supercapacitor buses. And Nigel said to me, you know, there's one problem with these buses, a traffic jam. Because if you get stuck, they're going to self-discharge and you're not getting home. So you have to have lithium ion as your backup. And it's interesting, it turns out, I have heard from one of the country's leading experts in supercapacitors, that the Chinese supercapacitor buses actually have a backup lithium ion battery in them. So I think that's worth pointing out. And here we have the existing applications. Obviously, transportation is the main one. The reason petrol has defeated batteries for the last 100, 150 years is the high energy density and the rapid refueling. We might be able to challenge that with a combination of our technologies that we have developed. And we think that the 26 watt-hour per kilogram is an extremely important number, because that, if it's low cost, will deal with the buffering of renewable energy systems, and also that container-sized huge supercapacitor that you're going to go to the petrol station and recharge from. Anything above that, the sky's the limit. And we have only scratched the surface. We do not know what is possible. We've literally made a breakthrough and we don't know where we're going in terms of the capabilities. We do actually know where we're going in terms of a company, which I will just conclude right now, but in terms of the science. So with the, well, our view is that we want to be able to get to a baseline electrolyte combination by the end of this year, and then build a low volume prototype production line having optimized the production route. And then we will be in a position as a company to decide whether to license our materials and the production technology, or to go into joint manufacturing with a third party, or go into high volume manufacturing, ideally with government support, building a gigafactory or several if the technology is good enough. So that's where we would like to take the company over the next few years, and we're very excited about it.